You're watching a Channel 98 NBISD TV production.
Hey, welcome to another fantastic episode, as always, of That Geometry Show. And as always, I'm still Kevin Corpy, your host of the show. Now, today I'm going to be leading you down a mathematical path filled with lots of sharp, pointy objects. So this show is going to be anything but dull. Actually, those sharp, pointy objects are triangles, right triangles to be specific. And we're going to take a special look at a ratio of two of the three sides of a right triangle with respect to a specific angle. So if that doesn't sound intriguing, I don't know what is. So grab those worksheets from the website, sharpen that pencil, roll up your sleeves, and we will triangulate. Lesson 30, the big 3-0 over the hill when it comes to episodes here now. All about trigonometric ratios, trigonometry. We're kind of scratching the surface of an entirely different field of mathematics called trigonometry. And we're going to look at basically three special ratios of right triangles. And it is kind of the basis of what we call trigonometry. Now, trigonometry is a branch of mathematics that is derived from two Greek words, which simply means angle measure. And today we're going to look at the ratio of two of three sides of a right triangle based upon something that we've talked about in the previous episode, a reference angle. So that's where the angle comes in. Now remember, in any given right triangle, we can label the vertices of the triangle as capital letters. So this would be vertex A, vertex B, and vertex C. And then we can represent the line segments or the lengths of the sides opposite the vertices as the corresponding lowercase letter. So if angle C is the right angle, we can call side C the longest side, which is the hypotenuse. Opposite angle B would be side B. And opposite angle A would be side A. So that's just working our way, our notation, working around the right triangle. Now we can say that any given triangle is dependent. That is, the size of it is dependent upon our independent choice of a reference angle. Assuming that the right angle is always 90 degrees, if we choose the size of one of these other angles, whether it's this angle or this angle, once I establish how much I'm rotating, and I draw my little line segments from my right angle, the line that's drawn to intersect this side here is going to predetermine the relative sides of all the sides of the right triangle. So we can kind of think of the size of this right triangle as a function of the size of this angle right here. And if this is the angle that I'm referring to, remember we call that the reference angle. So let's look at what we can call the side lengths besides their names A, B, and C in reference to an angle, which remember we use the Greek letter theta. Okay, so I'm going to start down here at angle B, and I'm just going to call it theta on the interior just for notational purposes. Okay, so if I'm going to look at a ratio of the two side lengths, since I have three sides, I can take them two at a time. And in which ways can I take two sides at a time when there's three? Well, in relation to this angle, I can take side B, which is the side that is opposite here, that's side B, and then I can look at the side that is the hypotenuse, which is next to it, but it's the longest side, that would be side C. So looking at the opposite side to the hypotenuse, which is B to C, is one way we can look at the ratio of two of the three sides. So we'd call that B over C is, in this case, the opposite over hypotenuse. We can also look at, in reference to this angle, we can look at the adjacent side. Now, adjacent is just a fancy name for next to. And if you look at this angle theta, there's actually two sides that are adjacent to it. But one of them is the hypotenuse. So when we say adjacent side, we mean the adjacent side that is not the hypotenuse. Okay? So I can look at the adjacent side, which is A in this case, to the hypotenuse. So that would be A to C right here. And then I can also look at the opposite side, which is B, in relation to the adjacent side, A, leaving the hypotenuse out of it. So those are three different ways we can take two sides of the right triangle. Now there actually are three more ways we can take the ratios, but they end up being just the reciprocal of these. So instead of B over C, opposite over hypotenuse, I can equivalently look at the hypotenuse to the opposite side. But those three have different names, and you'll study more of those in pre-calculus. So today we're going to concentrate strictly on these three unique ratios. Okay? Now, they are ratios, and we don't want to have to call them B over C every time, or the opposite over the hypotenuse, and we definitely don't want to say, hey, you over there. So we're going to have to give these guys some really specific names, and that's where the trig ratios come in. So here's what I mean. Here's our little triangle again, just so we can refer back to it. When I look at a reference angle, and again, I'm referring to this as my reference angle, angle B, which I'm denoting as theta, the ratio that is the opposite to the hypotenuse, we name sine, S-I-N-E. We call that ratio the sine of theta. And we abbreviate it just S-I-N of theta. So we need the angle behind the abbreviation. And that angle, remember, represents kind of our independent variable. We choose independently what the angle is, and assuming it's a right triangle, the relative sides are predetermined. So opposite over hypotenuse we call sine. The adjacent over hypotenuse, which in this case was our A to C, we call it the cosine of theta. Co-S-I-N-E. Kind of the same base as that. And we abbreviate that as COS of theta. The ratio that is the opposite side to the adjacent side, we give a specific name of tangent of theta. And it also has an abbreviation, T-A-N, tan, with the angle behind it. So sine of theta, we read that. Cosine of theta and tangent of theta is how we read those. Now let's take a couple of seconds here to just note some things. We can refer to angle B as the reference angle, and we can also refer to angle A as the reference angle. But notice if I use this angle as my reference angle, the hypotenuse is still the hypotenuse, but now the side opposite right here becomes little a. Whereas if this is my angle B, that's the adjacent side. So it's really, really, really important that we are choosing a specific reference angle first and then setting up our trig ratios based upon that angle, because your opposite and your adjacent are going to switch. They're dependent on your choice of angle. Hypotenuse doesn't matter, it's always the longest side. Now, can the right angle be the reference angle? Well, not in geometry. In pre-cal, there's a special case where we can look at its ratios. But if you think about what we're doing here, if we call the right angle the reference angle, the opposite side would also be the hypotenuse, and then we would have two adjacent sides that weren't the hypotenuse. So the ratios would not really make sense. So we're going to limit ourselves right now to the study of reference angles that are one of the two acute angles in a right triangle. Okay, and we have to find it first and set up the ratios accordingly based on that. All right, let's look at this example. Okay, we want to find the three trig ratios, trig is short for trigonometry, for the following right triangle for angle A, and then we want to do it for angle C. So here we go. We've got a right triangle. We know we have that there. We have our three side lengths measured, and they could be in inches, they could be in feet, they could be in centimeters. I'm going to go ahead and include units here just to kind of show you what happens to the units. So I'm going to say that this is inches. Of course, it's not drawn to scale. Now, if I'm trying to find out the trig ratios for angle A, I want to clearly identify that that is my reference angle. So the side opposite it, boom, is my 5. The side that's adjacent is 10. And the hypotenuse, boom, is the longest side, 5 square root of 5. And remember, it's always opposite your right angle. So let's go ahead and fill in our ratios. Now, I'm not using theta here. I'm actually using A to represent the angle as well as the vertice. And that's commonplace to do that. So sine, remember, is the opposite, which is 5 inches, over the hypotenuse, which is 5 square root of 5 inches. Now, notice what happens to our units. Trig ratios are actually unitless measurements because the ratios, or the units in this case, inches, will always divide out. Now we're left with 5 over 5 square root of 5. But we can simplify that. The 5's will divide out, and we're left with 1 over the square root of 5. Well, we talked last time about whether or not we wanted that as our final answer. And in general, we don't like radicals in the denominator. So what we'll do is we'll multiply by a clever form of 1, which is the square root of 5 over the square root of 5. And if we multiply, we get the square root of 5 over 5. So that number right there, it's kind of an index, is a measurement of this specific triangle's vertical height, really, because it's the side opposite angle, to its hypotenuse. Okay? That's approximately 0.447 if you have a calculator. Let's look at the cosine of the same angle. Same angle, but now cosine is the adjacent, which is 10 inches, over the hypotenuse, which is 5 square root of 5. And again, I'm not going to write the inches because they're just going to divide out anyway. So again, a cosine ratio, a sine ratio, a tangent ratio is unitless. Now we can simplify. 10/5 is really 2 over the square root of 5. And getting rid of the square root of 5 out of the denominator, we rationalize it, and we get 2 square root of 5 over 5, which is approximately 0.894. And finally, looking at the tangent ratio, remember, was the opposite. So here's my angle A, haven't changed. The opposite side is 5 over the adjacent is 10. So tangent is 5 inches over 10 inches. The inches divide out, and 5/10, no radical this time, is 1/2. Okay? So those are the three trig ratios for angle A, sine, cosine, and tangent. Now what if I change my reference angle? Same triangle, same measurements, but now my reference angle is angle C. So I'm referring to that angle. The hypotenuse is still the hypotenuse, but now the opposite side is 10, and the adjacent side is 5, and like I said before, the hypotenuse is still h. So you can actually label them with O, A, and H. That might help you set up your ratios. Okay, so sine, remember, in relation to C is your opposite, which is 10, over your hypotenuse, which is 5 square root of 5. Well, we've seen that guy before. It's the same as the cosine of angle A. Well, we've already simplified that, so let's save a little time, and we'll call it 2 square root of 5/5. And the cosine of angle C now is the adjacent, which is 5, over the hypotenuse, which is 5 square root of 5. Well, where have we seen him before? The 5's divide out, and we get 1 over the square root of 5. So cosine of C was the same as sine of A. I think I'm beginning to see a pattern here. Tangent of C, let's look at that. Here's angle C. So the opposite side is 10, and the adjacent is 5. So this becomes 10 over 5, which is 2. Okay, which is really the reciprocal of tangent of A. It was 1/2 here, it's 2 here. And that's reasonable because the opposite and the adjacents will always interchange when you change reference angles. But I want to look at the sine and cosine values a little bit more closely here. First of all, notice that your sine and cosine are less than 1, 0.447 and 0.894. And that should always be the case when you're looking at the sine and cosine ratios. And if you're wondering why, let's go back to the definition here. Remember, sine and cosine were the ratio of the opposite or the adjacent, which are really our two shorter legs of our right triangle, to the hypotenuse, which in a right triangle is always the longest side. So if we have a small number over a larger number in the sine and cosine ratios, we will always end up with a fraction that is less than 1. So that's a good way to check yourself. If you end up with a sine or a cosine ratio value that's larger than 1, you goofed somewhere. You probably got your hypotenuse interchanged with one of the shorter legs. Now the tangent values can be greater than 1 because we're just looking at the ratio of the two legs, and they could actually, one could be larger than the other, it doesn't really matter. The other thing that I want to look at a little more closely here was what we noticed, that sine of A and cosine of C were the same value, and cosine of A and sine of C were the same value. Well, that is really not just a coincidence. That's always going to be the case. If you've noticed, we have the name sine, and we basically have cosine, which is just sticking a co in front of sine. And that word co has some very important meaning here. If you know in a right triangle that this is 90 degrees and the sum of all of them have to equal 180, that means the sum of the remaining two acute angles, in this case A and C, has to equal what? The measure of angle A plus the measure of angle C has to equal 90. That means that they are complementary angles. If you remember that from an early show. Complementary angles. Well, look at the first word there, or the first part of the word complementary. It's co. Well, that's exactly why sine and cosine are called co-functions. That's where the names come from. They're co-functions because the sine of angle A is equivalent to its co-function, cosine, of the complement of A, which in this case is C. Or the sine, we'll say the cosine of C, is equivalent to its co-function, sine, of the complement of C. So that's why they are called co-functions of each other. Okay, but again, more on that when we get to pre-calculus. Okay, now I know that seems like it's hard to remember, but there's an easy way to do it. There's a little mnemonic that's been around for ages. So you can talk to geometry students that had geometry years and years and years ago, and they're still going to remember this. It's SOHCAHTOA, which really kind of sounds like Archimedes as a podiatrist. Okay, what his advice would be if he was a podiatrist. SOHCAHTOA. There we go. This one isn't written on. SOHCAHTOA. Now what is SOHCAHTOA? Well, SO, S-O-H. S is for sine, O is for opposite, H is for hypotenuse. So the sine ratio is the opposite over hypotenuse. The cosine, C, is adjacent over hypotenuse, so that's how you get the ka. And toa, that means tangent, is the opposite over the adjacent. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. SOHCAHTOA, okay? Pretty easy. Now, if that's too easy for you and you want to kind of make it a little more interesting, there's a lot of other mnemonics you can make up. One of them that actually has been used quite a bit is some old horse caught another horse taking oats away, which I guess is good if you love horses. One of my personal favorites is some outhouses can actually have totally odorless aromas. I'd probably tend to disagree with that, but it's a cute way to remember SOHCAHTOA. All right, so we can really now redefine our ratios in terms of O for opposite, H for hypotenuse, and A for adjacent. Sine of theta is O over H, so cosine is A over H, ka, tangent is O over A, toa. Got it? Good. All right, let's take a quick break, give you some time to resharpen that pencil and to find that Epsom salt that you're going to need for that good toe soaking. But hurry right back, don't go too far, because we got a lot more problems that need to be calculated.
Yesterday, my friends told me to smoke some pot, and I did. Then today, they said I should try and fit my fist into my mouth. It fits, but I can't get it out. I'm an idiot. I'm under the influence of others, and that ain't me. That's what he said.
Live above the influence. Above them, above weed.
Welcome back again to That Geometry Show. I'm still Kevin Corpy, and today we're talking about ratios of right triangles, sine, cosine, and tangent. And we just learned a nice convenient way to memorize them, the ratios, which sides go with which name of the ratio. And now it's time to put those to use. Let's work some problems. Okay, so let's put SOHCAHTOA to good use. I'm going to write it again up here. SOHCAHTOA. Real easy to remember. Okay, now you have a visual that you can look at to help you set up your ratios. Here it is. We got a right triangle. We know it's a right triangle because we can see the little box right there. And of course, what would a math class be without finding x? So there's x. It's one of the shorter legs of the right triangle. We're given 25 to be the hypotenuse, and we know that this little angle here is 32. So if you think about SOHCAHTOA, we have an angle and two sides. So I have to know two of those three in order to find the third. We can use them like formulas. So let's go. We're given one angle. That's not the right triangle. So there's 32. And let's see the side lengths that we have. We're given the hypotenuse, and we're trying to find the side opposite. So if you're looking for a sine, here it is. We've got an angle, the reference angle, opposite over hypotenuse. So I'm going to write the O and the H, and which one does that go with? That's so. And so means sine. So that's an easy way to help you figure out which ratio to use. So now we'll set it up. Sine of my reference angle, 32, is equal to the opposite side, which we're calling x here, over the hypotenuse, which is 25. We have now set up a little equation. Well, to solve for x, I just multiply both sides by 25, and I get x equals 25 times sine of 32 degrees. Now, let's talk about calculators for a little bit. Your calculator does have a sine button, a cosine button, and a tangent button. But there's two different ways to measure angles. You can measure it in radians or degrees. We're going to be using degree modes strictly in geometry class, so you want to make sure that on your mode function, you are in the degree mode. Otherwise, you're going to get the wrong answer. The other thing is when you hit the sine button, it automatically opens up parentheses for you right there that it's a good habit to get into closing it right there after you input your angle. You don't need to put anything between your 25 and the sign. So you can type it as 25, hit the sign button, 3-2 in degree mode, close parentheses, and then hit enter. And then your calculator will give you your approximation, 13.248. If you're in the wrong mode, it's going to give you another answer, and there's not going to be really any way for you to know that you're in the wrong answer, you're in the wrong mode, unless you get an answer that's really, really unreasonable. Okay? So just check your mode first. Make sure you're in degrees. All right, so in that case, we use the trig ratio to find a missing side length. We can actually complete the rest of the triangle. We can find the third side length now, since we know this right here to be 13.248. Remember the theorem that we can use to find the third side length if we know the other two? We can use the Pythagorean theorem if we wanted to, once we know that side, to find this. Or we can actually set up another ratio, another trig ratio, which I'm kind of excited about doing. Let's see what we get. Let's do that. I'm going to use the same angle 32, and now I want to find this side, which is the adjacent side to it. And I could use the side I just found, 13.248, but I've rounded, and I don't want to have a rounding error, so I'm going to go ahead and use the nice integer 25 that was given, which is still the hypotenuse. So now in relation to 32, that's a and h, I can set up another ratio. Cosine of 32 is my unknown side length a, and I'll just call it a, over the hypotenuse, which is 25. And if I solve for a, I get a equals 25 cosine, open parentheses on your calculator automatically, 32, close them up, and then you can punch that in, and I believe you'll get 21.201-ish, and you could verify that by using the Pythagorean theorem. And one last question here. I didn't ask for us to find this, but I'm just kind of thorough. Can we find what that last angle is? Well, yeah. It is the complement of 32. So 90 minus 32 is 58. And once you know all three sides and all three angles of a triangle, you have basically, let me try and spell that right, you have basically solved the triangle. So you consider the triangle solved. Mystery solved. Nothing left to find. All right. Let's look at another way we can use the ratios that's different from finding a missing side length. This example involves finding a missing angle measure. So again, in order to use the trig ratio, sine, cosine, and tangent, we have to have a right triangle. So look for that first. There's our little telltale sign right there. Got a right angle. We know this side is 8, this side is 7, and we're trying to find this angle, angle Z. Well, that's the only angle that we're given besides the 90, and so I'm going to call that my reference angle. I need to know two sides then. Well, in relation to angle Z, that's the side that is opposite the angle, and 7 is the adjacent side because it's not the hypotenuse. So O and A, which one is that? Let's see. So OH, no. Ca, AH, no. TOA, OA, there it is. Well, TOA is tangent. So we set it up. Tangent of angle Z is equal to the opposite, which is 8, over the adjacent, which is 7. Now, we got to talk about how to solve this on your calculator. Previously in an algebra class, if you're trying to solve for a variable, like let's say you had 2x equals 4, you're currently multiplying your x by 2. The inverse operation of multiplying by 2 would be to divide by 2. So dividing by both sides undoes the multiplication, and that's what allows you to isolate your x. Pretty easy. But what's the inverse operation of taking the tangent of an angle? You don't want to divide by both sides by tan, so what you do is you take the inverse, or the arctangent. I'm going to use the inverse notation. So if I take the inverse tangent, and we denote that by putting a little -1 up here. The inverse tangent of both sides, whatever we do to one side, we have to do to the other. And inverse tangent is an operation, so we have to take it on the left-hand side. Now, guess what the inverse tangent of tangent is? Inverse operations always undo each other. So if we start with Z and we apply two operations, they're going to undo each other. We're going to be left with Z. And so we have tangent, or Z equals the inverse tangent of 8/7. This is something we can actually do on the calculator. Your calculator has an inverse tangent button. If you hit the second command and then hit the tangent key, you basically have this appearing on the calculator. It'll have little -1. So again, if you're in degree mode and you type in second tangent, parentheses are going to open, 8 divided by 7, close them up, and hit enter, you're going to get an answer of 48.814. And since we're in degree modes and that's an angle, we're going to put a little degree symbol there. So inverse trig functions. The inverse operation of taking the sine would be the inverse sine. Taking the cosine, the inverse would be the inverse cosine, which is your second command key on your calculator. Get used to it, get comfortable with it. Now it's time for the say what? And there's a lot of applications of right triangles. We're going to look at two today. Hopefully we'll have time to do both of them. Here's the first one. From the top of a 150-foot air traffic control tower, a controller spots a jet at an angle of 42 degrees above his line of sight. If the controller's radar shows, and this is a radar right here in case you're wondering, if the controller's radar shows the jet at an altitude of 2,600 feet, how far is the jet from the control tower? Well, word problems have a lot of words in them. That's why we call them word problems. We need to make sense of what's going on here. Okay, I read in there somewhere that we've got a control tower that's 150. So I know this is 150 feet. And there's a controller up here. And if we draw a horizontal line of sight, it says that he's looking up at this plane right here. And that is our angle of elevation that we talked about on the previous episode. That's what's 42 degrees. We also know that the jet is 2,600 feet above the ground, not above the tower. So this distance here is 2,600 feet. This forms a right angle right there. We're trying to figure out how far is the plane from the controller. So I'm going to call that h right here because it's this distance and it's the hypotenuse now of this right triangle. Well, I need to know, I have the reference angle. I'm trying to find an unknown side, so I need to know another side length. How am I going to do that? Well, if I know that this total distance is 2,600 and from here to here, remember, was 150, all I have to do is subtract those two and I can get the height basically of this triangle, which is this right here, and it comes out to 2,450 feet. Now I have my side lengths. I'm ready to set up my ratio. This is the opposite in relation to 42, and I'm trying to find the hypotenuse. So O and H is sine. So sine of 42 degrees equals 2,450 feet over H. And if I solve this for H, I have to do a little bit more algebra, but I get H equals 2,450 divided by sine of 42 degrees. And if you do that, you get 3,661.467 feet. And that's basically the distance from the controller to the plane as the crow flies, or as the plane flies right through the air. Here's another example that we're not going to have a chance to work through all the way, I don't think, but it's surveying. Surveying uses a lot of triangles. We've got a surveyor, and he's taking readings from one part on the shore, and he's going to be able to figure out how far across it's going to be to get from one bank to the other without getting wet, which is kind of nice. All he does is he sets up his tripod or theodolite, and he uses his transit to take an elevation to point B, which he finds to be 64, and then he can measure this distance along the shore that he walks, 200 feet, let's say. He'll reset up his transit, and he'll shoot a measurement over here, and that's a right angle. So just by knowing this, he can figure out what this is. I'll help you get it set up. Here's 64. We're trying to find the distance, which is really the opposite side, and we know the adjacent side. So that's O and A. That's going to be tangent. So tangent of 64 is O, which is representing the distance across the river to the adjacent side, which is 200. So the opposite side, O, is 200. Tangent of 64, which if you work that out on the calculator, you get, let me see, on the calculator, here it is, you get 410 feet across. I said we wouldn't have time to work it, but we did. 410 feet, which is approximately 2,050 toes. All right. Hey, speaking of toes, we just got our toes wet, really, when it comes to the broad and diverse applications of right triangles. Something that I hope was interesting for you, and something that you will hopefully get a chance to study in more detail when you take pre-calculus sometime in your high school career. Okay, but until next time, since we're out of time, I'm Kevin Corpy, reminding you that some outhouses can actually have totally odorless aromas. And I'll catch you on the flip side.